Thank you, Jim. It sounds to me like you're going to need to go out and find a new textbook to teach all those students about what elements are used to build life.
Well, I don't know about a whole new textbook, but certainly some paragraphs and sentences are going to have to be rewritten as of today.
I'm at the beginning of my career, so see you on the back end of that.
Okay, Felice, I'll be happy to review it. I'll get started.
Great. Thank you, Jim. Our next speaker is Dr. Stephen Benner, from the founder and distinguished fellow from the Foundation of Applied Molecular Evolution. And he spent a lot of his life as an organic chemist and studying the chemistry of life. What are your thoughts?
Well, I'm the curmudgeon here. I'm the chemist who has been brought in, as Felisa knows, to throw wet blankets on things and to try to dampen a little bit the enthusiasm. My next 3 minutes will be successful if I convey to you folks why chemists think that this is an exceptional result, and why, therefore, chemists will, like Carl Sagan says, require exceptional evidence to support it. And I also want to make sure that you folks understand why we nonetheless find it interesting. What Felisa has found, of course, is a microbe that grows in the environment which has a lot of arsenic and very little phosphorus. The Astrobiology Institute, which we are parts of, is the one place in American science where you can go to find geologists and microbiologists and astronomers and chemists together, where we can have the productive clash that leads to big discoveries about big questions. What is life? What could alien life look like? And so my goal in the next 30 seconds or so is to try to give you, as a layman, the understanding of how this is an exceptional result, how it might be looked at in greater detail, because one thing that will survive is the Felice's microbe, and that will be an excellent system to explore questions about how arsenic is tolerated and phosphorus is limited in organisms that are placed under environmental stress. So I brought my Richard Feynman props with me, which is a representation of a molecule, right? And these molecules are, say, representing a biopolymer, and of course we're making them out of steel, and the result is it's tough, right? And of course, as Felisa has mentioned, arsenate is made out of, in this particular case, aluminum foil. And of course, it's not as tough as steel, but when a bacteria is going to try to form a new chain, it's going to try to find in the environment the links that go to form the chain. And of course, if there's arsenate around, as a weak link, it will maybe confuse and maybe deceived by the structure of arsenate and the similarities to join two chains together, not by a steel chain, but rather by an arsenate chain. And of course, these are compounds that have been studied in model form. The specific arsenate DNA has actually never been isolated, but there are compounds that are similar to it. Different kinds of atoms, but still carbon, oxygen, arsenic, oxygen, carbon linkages. And so we know that they're relatively unstable. They fall apart with half-lives measured in the order of minutes, conveniently. And so when you try to put them into a DNA molecule, right, and then you put it under stress, they fall apart, and then of course your biological system says, oh my God, I've just destroyed my molecule, I got to go back again. So again, if there's arsenate in the environment, right, you can get the story, you waste a lot of energy and a lot of time trying to put into DNA backbone arsenate, where if the arsenate ester falls apart, you're effectively saying that arsenate is the, I guess we call it the wolf, demon wolf, or demon sheep in sheep's clothing. It fools the enzymes into taking it instead of what it should take. There are two ways that biological systems in general can manage this. One way, of course, is to get very good at distinguishing between sheep and wolves in sheep's clothing, and therefore the end result is, of course, that you don't get fooled by the analog. The other possibility is also conceivable that the biological system can have evolved to manage the weak link, and they might manage the weak link by, for example, binding something to the weak link, sequestering it, keeping it tight. But the difficulty that we're having, or in fact almost anybody with chemistry who is familiar with this literature will say, well, wait a minute, this DNA molecule has allegedly been isolated away from the other molecules in the biological system. So we remember all this old chemistry, and we don't believe it. And that's what you're going to see a lot of people say. Now keep in mind, old chemistry can be wrong. And in fact, one of the wonderful things about being in a science is, as Richard Feynman would say, science begins when you distrust experts. And of course, as the expert in chemistry, I'm saying that you should distrust me. But the bottom line out of all this is that what you're looking at here is an exceptional claim. based on the context of the chemistry. And of course, when we can go into great details about what experiments you might do in the future to explore this, but what PhilESA has produced is a very, very useful system to ask these kind of questions. One last point. Remember, the weakness of the link is a weakness measured at room temperature, 35, 37 degrees centigrade, 98.6 degrees Fahrenheit, in water. If you go to an exotic environment, and the National Academy of Sciences produced a book, which is actually you can go have, it's coming out of the National Research Council, called The Limits of Life in Limits of Organic Life in Planetary Systems. You realize that in our solar system there are places, Titan, a moon of Saturn is one of them, where the temperature is much lower, where very reactive species like arsenate could very well be useful because, although they're too unstable to exist in many environments on Earth, they're not too unstable to exist in an environment like Titan, which is at minus 290 degrees Fahrenheit. So it's a cold environment. In fact, you might very well want to have the increased reactivity of arsenate in that environment just to get the reactions as you want to make your biopolymer chains go a little bit faster. So, again, my role as the curmudgeon is to say, this is an exceptional result. I hope I can convey to you a little bit, maybe not in technical language, but in graphic language, why the chemist views this as an exceptional result. And so you will understand why in the NASA astrobiology program over the years, as these various disciplines of chemists and who are the doubters or the deniers, the microbiologists, the geologists will interact in a way to bring forward the process that science is, which is, of course, the clash of contradicting cultures in an effort to come up with the truth, to inspire, of course, Americans' youth to go through the effort of studying science, so they, knowing full well that there are these kinds of very interesting questions out there, like what is life and where might we find it, if not on Earth.
Thank you, Steve. I have a question for you. So, would you as an organic chemist consider replacing your graduate students with microbes?
There
to
are
explore these reactions.
Many of my graduate students are undoubtedly watching, and I love you all, and I wouldn't think of replacing them.
Fair enough answer. Okay. Our next speaker is Dr. Pam Conrad. She's a planetary scientist at the Goddard Space Flight Center and also the deputy PI in an investigation that will be flown on the Mars Science Laboratory to be launched in a year from now. It's the first astrobiology mission since Viking, and whose goal is to look for evidence of habitability and the potential for current and past life on Mars. Please, Pam.
Well, I don't think I'm going to classify myself either as curmudgeon or otherwise. My role in the astrobiology spectrum is to think about how we might predict the habitability of environments off the Earth. And the way I go about that is to see what I can learn about environments on the Earth and try to develop metrics for habitability. So I find this result delightful because it makes me have to expand my notion of what environmental constituents might enable habitability. So, for example, if you just think about an environment in terms of what it's made of and how those things are arranged, you have a concept of an environment just like the chemical environment. Everything is a function of its constituents and how they're arranged. So what is really interesting about this result is if you can make a biomolecule that has substitutions in it, the properties have to change as a function of new constituents. So it opens up a whole new line of questioning. What might those changes be? What do they portend for the evolution of that chemistry? What do they mean about the environment? And by the same token, we might learn something new about habitable environments by understanding how organisms that are there adapt to the presence of new or limited chemical constituents. With respect to space exploration, this is a very interesting result again, because the implication is that we still don't know everything there is to know about what might make a habitable environment on another planet or a satellite of another planet. We have to increasingly broaden our perspective. So perhaps arsenic is not an essential component for habitability or for life, but it may be one that can be tolerated, and that opens up our perspective to try to understand what other potential components might be tolerated, or in fact even essential, that we presently haven't thought of.
Very much. So I'd like to bring this all around and back to PhilESA, for her to put her findings in a broader context for us and remind us of exactly what they are and their importance. So let's
remind us what we've learned here today. I'm interested in exceptions, and I think many of us are interested in those exceptions to the keeps me up at night. Why? I was probably a very difficult child in junior high and high school. But what I'll say is that that kind of openness to questions is part of what I want. I hope that the work of myself and my team that produced this, and I want to really reiterate it, it's not about arsenic, and this isn't about Mono Lake. It's about thinking about life in a planetary context and asking questions, simple questions, with a simple experimental design. And so, in like a bigger scale, let's go from the small, and then we'll go into the abstract. All life on Earth required carbon, nitrogen, oxygen, hydrogen, phosphorus, and sulfur. So I've shown here today that we've discovered a microbe that can substitute arsenic for phosphorus in its major biomolecules. Not just DNA, but things like ATP, that many of those high school students out there I hope recognize, and also all sorts of other biomolecules. What does that suggest? It cracks open the door to the potential. You know, my niece asks me, how did we get here? And are we alone in the universe? And it's profound that we don't know the answers exactly to that yet. Maybe not in my lifetime, but maybe in her lifetime, she'll be able to answer that. But I hope my work serves as a proof of concept that we can experimentally test and show evidence of what else is possible. So I'd like to roll some footage just to give us the expansive nature of life, from microbes to crustacea, to bugs, to mammals, to everything you know that's alive on planet Earth. Again, hearkening back to the idea of the pale blue dot. Understanding life here, all sorts of life, lions and tigers and bears. And how everything we know is on this tree of life. Everything you've ever thought of so far that we can see on this tree of life. So what we're presenting here today is a member of this tree of life. We're cracking open that door. Strain GFAJ1, the bacterium, is a different way to do business. Just to open the possibility to what else is possible. It has solved the challenge of being alive in a very different way than we knew of. What other questions can we ask? This will inform us about life on our own planet, and it will help inform us of life. We will find it one day elsewhere in the universe. Thank you.
Thank you very much, Lisa. And I'm going to turn it back over to you, Dwayne.
Thank you all. And Felisa, congratulations to you and your team. Okay, ladies and gentlemen, now we get to the question and answers to really even flush it out even more. We're going to start here first and then go to the West Coast. I'm going to ask you to wait for the microphone, give your name and affiliation, and obviously we have folks here, and we also have a professor in Arizona, so if you can address your question to the appropriate person, that'd be great. Let's start with Mark Kaufman.
Thank you, and congratulations. What I'm intrigued by and trying to understand is you refer here to substitution of the arsenic. Is there reason to believe that this was substitution that occurred in any kind of a time frame, or is it possible that this is something that has been in the bacterium or in other bacteria going back to the beginning of life?
And I think, we'll have the next 30 years, at least in my career, and many others too, to begin to probe that. I think what it does suggest, I'm saying substitution, because we really just want to open this package to be able to think about what else life could be. And as an early career scientist, I think that's a safe way to go. But in terms of whether, I think if it just happened recently, substituting for what was, or how old this is, I think we can begin to address those questions. There's a number of experiments I can think of, and I know many of my colleagues who have been familiar with this work for a number of months now have suggested. What we can say, and dangerously to speculate just a little bit if you let me, is that phosphate, and it's phosphate in biomolecules, so phosphorus, and I'll go between those, you'll have to pardon me, on Earth is locked up in rock. So your bones are made of phosphate, because it's a good idea. And it's very, one of the reasons it just doesn't do a lot of chemistry. And in fact, I hope that Steve would agree in that phosphate chemistry is very difficult.